Biorefinery System Module 11 Lignocellulose Biorefinery Process Engineering Part 1 Segment 3 Transfer and Steam Explosion Process. With me, Yusuf from Bioengineering Study Program, School of Life Sciences and Technology, Institut Teknologi Bandung. Previously, we have discussed about heat and mass transfer in porous media and transfer in solid-state fermentation. In this segment, we will discuss about heat and mass transfer in steam explosion process. Steam explosion is considered as an effective pre-treatment method of lignocellulose. Explosion intensity is the most important parameter of steam explosion and directly determines the effect of lignocellulose pre-treatment. Commonly, explosion intensity is characterized by an intensity factor or modified intensity factor of the hydrothermal pre-treatment process. The effects of the steam explosion technique on lignocellulose structure can be summarized into two aspects. In the high temperature cooking stage, hemicellulose is degraded, lignin is softened, and cellulose is exposed. Second, in the instantaneous relief phase, superheated state water flashes into steam, causing an instantaneous expansion. Then a strong impact force on the material, resulting in tissue tearing and fiber loosening. The intensity factors summarize the influence of time, temperature, and acid concentration. Although it is easy to compare the experimental results, and the intensity factors to be applied in the process design and operation, the intensity factor does not summarize all the factors that influence the pretreatment effects. Unlike some other hydrothermal pretreatment technologies, steam explosion as an efficient component separation technique is notable in that its physical tearing impact is not only conducive to strengthening the lignocellulose fiber solution, but also increasing the specific surface area. Physical tearing is affected by many factors, including particle size, loading factor, and material moisture content. In addition, the design parameters of the steam explosion tank also affect the tearing effect, such as the ratio of height to diameter, the discharge port area, and the buffer tank volume. And of course, the dimensional pressure and temperature cannot be ignored. Model assumption. It is assumed that the material density does not change with vapor infiltration, and the buffer tank is large enough, which means that the pressure of the buffer tank is constant. Therefore, the variable parameters are dimensionless pressure, time, particle size, and moisture content of materials and relief port area. Efficient physical tearing occurs at the cellular level, which means each cell can be treated as a microgas blast pot. For details about the model as well as establishment of the material brittle fracture criterion and establishment of conservation equations, students may refer to Lignocellulose Biorefinery Engineering Principles and Applications, authored by Chen et al. 2015. Moisture and the pressure are key factors affecting the physical tearing in steam explosion. The Antoine equation is widely used to calculate the saturated vapor pressure. However, saturated water vapor pressure and temperature conversion are difficult due to their complexity. Therefore, a simple quadratic equation can be used to characterize the relationship between saturated vapor pressure and temperature. The discharge port area is related to the particle size under certain temperature and moisture content. This means that the material in different particle size require matching to different discharge port areas, whereas a fixed discharge port area should correspond to the appropriate particle size to achieve optimal physical tearing. Thus, material particle size for steam explosion is not randomly selected, but should be limited according to the discharge port area. Based on the material particle size, discharge port area, and material moisture content, a new steam explosion intensity factor can be calculated. The new steam explosion intensity factor R contains material parameters such as particle diameter and initial material moisture content, operation parameters such as temperature and time, and device parameters such as discharge port area, which not only helps to explore the steam explosion mechanism, but also provides a scientific basis for steam explosion process design. R would provide theoretical guidance for the steam explosion process and experimental design. For the next module, we will discuss about lignocellulose biorefinery engineering. Part 2. Until then, I am Yusuf from Institut Teknologi Bandung.